You tap Buy Now on a screen. You double-tap a photo to leave a like. You hit Submit on a bank transfer. As a user, it feels as though your device is executing these commands. But none of those visible actions are doing any actual computational work. The buttons, forms, and animations on your screen are entirely hollow. They are merely mechanical triggers designed to signal a separate, invisible system operating far away from the glass in your hand. That invisible machinery is built through backend engineering. It is the discipline of constructing the logic, the computation, and the physical infrastructure that powers everything a user experiences but never directly touches. Modern software design relies on this intentional split. We create a clean, minimalistic illusion on the surface for the user to navigate, while concealing the dense, complex underlying reality of the machine doing the heavy lifting. Curious, analytical, to see how these requirements dictate the shape of modern software, we can run a brief thought experiment. Imagine an application built entirely without a backend, existing solely on your local device. Suppose you download a locally hosted to-do list app. You spend 20 minutes typing in several critical deadlines and highly detailed project tasks. This setup fails immediately. The moment your browser refreshes or your operating system closes the app to save battery, every piece of data you entered is permanently annihilated. Local hardware memory is inherently temporary and untrustworthy. For software to be useful, it requires state persistence, a durable, centralized location where data survives beyond a single user session. Once you scale this limitation up, the architecture collapses entirely. Without centralized persistence, a messaging app has no central post office to route a text from your phone to a friend's device. A banking network cannot verify your account balance if you walk across town and attempt to use a different ATM, because your local device holds the only record of your deposits. An e-commerce platform cannot track a shared inventory of physical goods because thousands of shoppers would be operating in isolated, local realities, completely unaware of what others are purchasing. A zero backend architecture results in isolated routing, zero security against manipulation, and total amnesia the moment a device powers down. Large-scale software demands a singular, authoritative source of truth. It requires centralized memory and coordination that cannot safely reside on the user's personal hardware. Moving the application logic off the user's hardware solves the memory problem, but it also addresses a much more dangerous vulnerability: control. Whoever holds the physical device has absolute power over the code running on it. If an e-commerce store calculates prices locally, a malicious user can simply open their browser's developer tools, inspect the code, and rewrite the price of a laptop from $100 down to $0. This diagram illustrates the strict architectural split designed to prevent that scenario. It is called the trust boundary. On the left, we have the client side, the user's device. Because we do not own this hardware, we must treat it as a permanently untrusted environment. On the right is the server side, where we maintain total control. When the user attempts to execute their manipulated purchase, the request leaves the untrusted zone and attempts to cross the boundary. It immediately hits a rigid validation check on the server side. The backend checks its own secure database, sees the true price is $100, and instantly rejects the transaction. This establishes the core rule of modern software architecture. The front end can only ever suggest an action. The backend holds the absolute, independent authority to decide what actually happens. The backend acts as an authoritative gatekeeper, protecting the application's integrity from the inherent risks of the user's local environment. We can see this gatekeeper in action during any high-stakes, real-world operation, like withdrawing $50 from an ATM. You punch in your PIN and hit withdraw. Let's freeze time at the exact millisecond your request leaves the machine. Look at this data flowchart mapping the transaction. The payload first strikes the API gateway. This is the defined doorway through the trust boundary, the only legal entry point into the backend. Once inside, it hits the authentication and authorization phase. The system verifies your cryptographic identity, confirming you are exactly who you claim to be, and checks your account permissions to ensure you are allowed to withdraw funds. Next is the business logic phase. The system runs the non-negotiable mathematical rules, checking your requested $50 against your total available balance to ensure you have the funds. Upon passing, it reaches the database interaction phase. The system permanently updates the financial ledger to reflect the new, lower balance. Only after this record is secured does the server send the command back to the ATM to dispense the cash. Wrapping this entire sequence are strict security and error handling protocols. If the bank's network drops exactly halfway through this process, these systems ensure the transaction fails gracefully, voiding the withdrawal rather than debiting your account for money you never received. The backend is never a single server box sitting in a closet. It is a highly specialized sequential assembly line that rigorously enforces the truth before any transaction is allowed to complete. This assembly line reveals a major misconception for those new to software engineering. You will often hear backend development described simply as writing APIs. The API is the communication layer, it is the doorbell. The actual engineering work is designing the sprawling industrial complex that sits behind that door. This is why front-end and back-end engineering require entirely different mindsets. A back-end engineer operates completely devoid of visual output. Their mental model is hyper-focused on data integrity, defensive security, and ensuring the architecture remains highly reliable even when 1 million users hit the system simultaneously. This discipline powers the invisible infrastructure of the modern internet. It manages the real-time routing of global messaging apps, balances international financial ledgers, organizes terabytes of video streaming metadata, and processes telemetry of connected devices. Behind every application is a persistent, trusted, logic-driven engine. Every pixel you see, every smooth animation, and every confirmation screen on your local device is merely a reflection of the authoritative decisions made safely behind the trust boundary. We know why this invisible engine exists and why it must remain isolated from the user. The next step is understanding exactly how the untrusted client manages to communicate with this fortress over the open web.
Look at the devices we use every day. They are physically isolated from one another, separated by miles, continents, and oceans. Yet, when we use them, we expect to inhabit a single shared reality. In the earliest days of computing, this wasn't an expectation. Programs ran entirely on a single machine. There was no concept of asking an external computer for information. But imagine trying to run a modern financial system with isolated hardware. If one node processes a transaction and updates a bank balance locally, the rest of the network remains completely blind to that change. To function, real-world applications require centralized data. Multiple users accessing a shared system need to see the exact same values at the exact same time. If every device is forced to hold its own disconnected copy of a shared dataset, the system inevitably fractures. Updates clash, balances diverge, and the data becomes instantly corrupted. Attempting to synchronize changes across hundreds of local copies creates a coordination problem that quickly becomes impossible to manage at scale. To maintain a reliable state, the architecture must designate one specific node as the single source of truth that all others defer to. The client-server model provides the structural blueprint for maintaining that single source of truth. This model defines a logic-driven pattern of communication. It establishes the rules for how two machines exchange information, regardless of their physical location. At its core, the pattern relies on a rigid mechanism, a continuous request-response loop between two clearly defined roles. This precise loop governs nearly everything you interact with digitally. It powers web browsers, drives mobile apps, database queries, and APIs, all relying on this exact framework to share information. These invisible request-response loops are the mechanism that keeps the world's data synchronized across billions of disparate hardware. To understand how this pattern operates, we can look at an abstract model. Here are two distinct software agents, floating in empty space with no active connection. The first role is the client. By definition, the client is always the initiator of the interaction. The client only needs to know how to ask for data. It remains completely blind to the internal mechanics of how the target actually processes that request. When you open an app or type a web address, the client generates a message and fires it out into the network. This vector is the request. At the receiving end of that vector is the server. The server's role is to listen and process. It waits for incoming vectors, executes the necessary business logic or database lookups, and prepares a targeted package of data. Once the processing is complete, it fires a response vector back to the waiting client, closing the interaction loop.
These terms, client and server, are purely behavioral definitions. They describe who asks and who answers, independent of the hardware they run on. In reality, that abstract request vector travels across thousands of miles of physical network infrastructure, routing through switches and undersea cables. The moment it hits the destination server, the software immediately begins processing the input, compiling a payload of HTML files, formatting JSON data, or preparing raw images. That specific payload is then packed into a response vector and fired back across the continent to the exact origin point. Upon receiving the payload, the client executes its local task, like rendering a complete web page or updating a mobile interface. Modern applications feel instantaneous because global networks are highly optimized to execute this massive physical round trip in a matter of milliseconds. There is a pervasive misconception that a client is strictly a laptop browser and a server is a rectangular metal box sitting in a refrigerated data center. Because these are behavioral roles rather than physical objects, these states are transient.
They shift instantly depending on the interaction. Consider a standard e-commerce checkout. In this diagram, a laptop browser acts as the client, sending a purchase request to the application's backend server. The backend receives the request and processes checkout logic. But to finalize the transaction, it needs to verify the card with an external provider. To do this, the backend must initiate a new outward interaction to a payment gateway. The moment it generates that new request, the server becomes a client. The initiator of a request can be almost anything. Devices like smart thermostats, networks of external servers, and command line tools like curl all act as clients when they ask for data. Furthermore, these roles aren't inherently split between different companies. An organization frequently builds both the client app on your phone and the server backend it talks to.
Defining a server by its physical hardware limits an engineer's ability to design dynamic, interconnected microservices. While centralizing logic solves the synchronization problem, it creates a significant engineering bottleneck: traffic volume. This introduces the concept of concurrency, a system's ability to ingest and process massive amounts of simultaneous incoming requests. Take a major platform like Instagram. This diagram illustrates a central backend cluster absorbing an overwhelming barrage of requests from millions of external nodes at exactly the same time. During a viral event, millions of independent users trigger discrete request-response loops, all trying to access or update the exact same underlying dataset. Amidst that chaos, the system must maintain extreme precision. It has to isolate each individual request vector, fetch the specific data packet, and route an independent response back out to the correct user. The stability of modern applications depends on back-end systems built to manage this massive concurrency without triggering data collisions or system failure. To clearly see the boundaries of the client-server model, we have to look at its direct architectural opposite. That alternative is the decentralized peer-to-peer, or P2P, system. This comparison shows the structural layouts. On the left is the centralized hub-and-spoke topology of a client-server system. On the right is a decentralized mesh network. In a pure P2P network, there is no centralized authority. Every participant acts as both client and server simultaneously, trading data directly with surrounding nodes. This structure is highly resilient and serves specific utilities well, particularly in distributed file-sharing protocols like BitTorrent. While peer-to-peer networks have their place, they lack centralized control. The vast majority of modern engineering requires the predictable centralized authority and the single source of truth that only the client-server model provides. We started with the problem of distributed computing, isolated hardware demanding a singular, shared state. The solution requires centralizing logic into a specific processor role, which eliminates the risk of local data corruption. When we map this out, isolated nodes snap into an organized hub-and-spoke layout, bound by high-speed request-response vectors. This topology relies on the relationship between initiator and processor. It establishes a single source of truth, scaling by managing high-volume concurrency. These components are entirely defined by their behavioral software states, not the physical metal they occupy. Which leaves us with a critical engineering question. If a server is just a software role passing messages across a network, what exactly is happening inside the physical machines to make that software run? To answer that, we have to crack open the server block and examine the bare metal hardware, the operating systems, and the underlying software daemons that actually keep the internet alive.